Alright, okay calculus fans, what we have here is a short lesson on, here are our topics. There are average rate of change, instantaneous rate of change. The tangent and normal lines really aren't topics of this lesson. It's essentially average rate of change, instantaneous rate of change, and position, velocity, and acceleration. Okay, so that's basically what we're going over today, and I'm sorry, hopefully you're not looking at this on your phone. If you are, maybe that'll help. So so essentially what you're going to need for this is you're going to need a, obviously pen and pencil, your calculator, and just, be able to pause. Hopefully you can do that, pause and take notes as we go. Okay, so essentially what I start with is a plot. Okay, and I'm going to show you the plot real quick. There's our plot, and this is data, and I'm going to give you the data, and I want you to put it in your calculator. So everybody go to stat plot, make sure your plot's on, hit enter on it, make sure once again it's on, X is L1, Y is L2, and of course, my bad, let's go back. And of course we want our dots, those are easy to see, and we also want our equation to be blank. Okay? So here we go. Here's the data, and basically what I did is I did a falling object motion simulator, and it's just it's kind of corny. It's from the internet and whatnot, but it's accurate as a falling object. So let's take a quick look. All right. Oh, that's not it. Okay. All right. Yeah, it's kind of corny. But what it does is it degree of angle, which makes no difference to what we're talking about today. Initial speed 40 meters per second. The mass is 150 kilograms, which doesn't matter. All that matters is the initial speed. Where's the initial position? Well, the initial position is like 1.5 meters or something like that, and gravity. All right, the force of gravity. Yeah. So those are the variables that we're working within, and you don't have to remember any of that. Let's go back to, let's stay focused, okay? We're going to focus in on average rate of change, instantaneous rate of change. All right, I'm graphing this, and also using the average rate of change to estimate the derivative. Okay? Once again, let's stay focused. Don't think about too much as we go through this. Just think about what you need to do, and hopefully you can glean and understand some more from it. So let's take another quick look-see at our thing. Score. What I've done is, what you're going to put in your calculator is let's take a look at this first. Okay, so what we have here is some fancy schmancy physics equations, right? And I pulled this off the internet, and I did a bad job because some of these equations are actually wrong. If you take a look at this, this is the position function for a falling object model, on the Earth, okay? It says x naught plus v naught. There should be a t right there, doggone it, plus 1/2 the gravitational constant times t squared. It should be written as this, okay, right here. X of t equals 1/2 gt squared plus v naught times t plus x naught. And you do not have to remember that, okay? Just remember this is a position function, okay? And a couple things for you non-phys-ies, okay? I'll call you fizzy-wizzies, you physics people, you non-phys-ies. The x of naught That's the initial position, v naught, initial velocity. And the 1/2 gt squared, that's just 1/2 times your gravitational constant. Let me go ahead and drop that on you. Gravitational constant is 9.8 meters per second squared. That's called the acceleration due to gravity. Alright? Now, I abbreviated a lot, I'm sorry. You kind of need to remember this equation just to be well versed. It's kind of one of those things that you need to know but don't need to know. Not for this course, but just in general. Remember this is called a position, falling object position model. And remember x of naught, v naught, and 1/2 times the gravitational constant times t squared. Alright, but there should be a t there, whatever this website is. Didn't have it, but I just pulled something off. Okay, so let's move on. Alright, so I said eventually we would get to putting data in our calculator, and here's the data right here. The x value is time. The y, oh, that's an ugly y. The y value is distance. Okay, so we're on a distance time graph. Okay, and I want you to plug these values into your calculator, and you're going to do it in the following way. Okay, let's see if y'all can see my calculator. You probably can't. Well, I'll just give you all those on my calculator here, so y'all can see it rather well. Okay. Alright, full screen please, thank you. Okay. Alright, so here I've already got it in my calculator. Go ahead, you hit stat, edit, enter, and go ahead and enter that data in. You can pause it, I'll give you a couple seconds. Alright, I'm about to move on for time's sake, so you need to pause it if you haven't already, and copy this data in your calculator. Also copy it on your paper here, okay? Alright, so there we go. I tell you what, while y'all are copying, I'm going to tear off some paper. And by the way, 7 and 8 are right there. Hopefully you've got, alright, 0 and 1, you need to pause if you haven't already. There you go, 1.2, 33.7, and then 7 and 8 right there. Okay. I'm going to tear off some paper so I can move. Alright. So once again, 0, 1. There. Okay. Type that data in. Of course, y'all have rewind capability, so I'm going to go ahead and move on ahead. In fact, I'm going to pause this real quick so I can get this data written down on my paper as well. So you may need to pause as well and do that. So it's just so I can shorten the video a little bit. I think I have to. Alright guys, and we're back. See, I've got my table here. I want you to copy this down. You've got this in your calculator. I want you to copy it down. Let me zoom in right here. Okay. Now, I've got my x's and my y's, and also I'm starting to calculate my average rate of change. Okay? Starting to calculate my average rate of change. And the reason I want to do that is because I want y'all to understand how to calculate average rate of change, okay, on an interval 0 to 1. Okay, we use this formula, f of b minus f of a over b minus a, which on this interval right here, 0 to 1, translates to on the bottom, b is 1, A is 0, so 1 minus 0, and then f of b is the y value at b, which is 1. B is 1. So what's the y value at 1? 33.7 minus 1.2. Okay, and what do I get there? I get 32.5 over 1. There, let me just write it right here. 32.5 over 1, which is 32.5. Okay, so it's kind of hard to see. Let me see if this will work a little better. Alright, that works a little bit better. So that's our average rate of change. Now you see, we cannot calculate, we don't have a formula per se to do an average rate of change. So let me go back and spiral back to that. Let's say f of x is equal to x squared, and we were doing the average rate of change on, well, we already know this, right? It's f of 1 minus f of 0 over 1 minus 0, which is 1 squared is 1, 0 squared is 0. I plug it in, yeah? I plug it in over 1 minus 0 and 1 over 1. And that really doesn't, that's not a good example. That's 1. Let's do the average rate of change. That's not a very good example. 1 comma 2. Not 1 comma negative 2, sorry. Okay, so that's f of 2 minus f of 1 over 2 minus 1. Alright, plug 2 into every x. 2 squared is 4, minus 1 squared is 1, over 2 minus 1. So the average rate of change is right there. Okay, it's there for you. Graphically, it would look like this. All right, here's 0, here's 1. My average rate of change is the slope on 0 to 1 is this slope. Okay, so once again, average rate of change on 0 to 1, that would be the slope. Rise 1 over 1. So slope of the secant line, secant just means touches 2 points, equals up 1 over 1 equals 1, right? Now what about 1 to 2? Seeing this is f of x is equal to x squared, alright, 1 to 2, that point would be 2 comma, what's 2 squared? 4, right? So graphically, once again, it would be a secant line. And what's that rise over run? Alright, this y value was 1, 2, 3, 4. So up 4 over 1. The slope of the secant line. And yeah, I'm sorry, that's not up 4, that's up 3. And yeah, you need to know that you can do this graphically too. It's 3 over 1. 3. You just look at the points. Average rate of change is easy, okay? Alright, we'll talk about instant rate of change in a second, but let's continue with this. What I want everybody to do is, I'm going to fill in these average rates of change. I'm going to pause it. I want you to copy those down. And then we're going to make our scatter plot and look at some things on our scatter plot, okay? So I'm going to pause it real quick and copy the average rates of change down. Alright, I'm unpausing here because I don't want to lose you. I'm copying down the average rates of change here. So once again, review average rate of change. The y value at 4 is 81. Alright, minus 74. Okay. 81 minus 74 is 7. Over 4 minus 3 is 1. so that's 7. Alright, y value 72 minus 81 over 5 minus 4 is 1, so that gives me -9. Alright, y value is 6, 57 minus 72 over 1 equals -15. And y value is 7 is 34 minus 57 over 1 equals, let's see, 34 minus 57 is 23 over 1, -23, -23. And then y value at 8 is 2, 34, 2 minus 34 over 1 is -32. Alright, so let's talk about what we're going to do with this data, but first, let's go back to our graphing calculator and let's see the original x and y on the, remember x is in seconds, y is in meters, okay? Okay, let's hit graph, and what you want to do is zoom and then hit 9, and it'll graph all those points nicely for you. So that's the x-axis is time, the y-axis is meters. Okay, so you can see at 1, 2, 3, 4, 5, 6, 7, 8, it basically hits the ground. Okay? Alright, so let's plot that on our papers, please. Okay? And essentially we're just going over 0 at 1.2, over 1 up to 33.7. The highest we need to go on the y-axis is 81. Alright, and we need to go 1 through 8. So go ahead and make that scatter plot real quick, guys. And like I said, for time's sake, I'm going to pause it a little bit, and you know, y'all can pause it as well if you need to. Alright, and we're back. I've got my y-axis labeled in meters, my x-axis labeled in seconds, and let's get rock and rolling, plotting these x's and these y's, okay? So 0, 1.2, 2, 1, 33.7, okay, 2, 59.8, somewhere in there, right? And then 3, 74, somewhere in there. Not really looking straight at it, so it's kind of hard. 481, 5, 72, 6, 57, 7, 34. I'm not the quickest grapher, I guess. 8 is very, very close to 0. Alright, so I want you to see this in a couple different ways, okay, guys? So there's our position, time, our distance time axis. I want you to think about what this slope really is, and this is one of the things we're learning. We're talking about position, velocity, acceleration, okay? Take a look at this rise over run and label it. In fact, let's label each one. Each one of these, y'all, is a change in distance over time. And as you see with the average rate of change, that's basically slope, right? It's the slope formula, which is basically a rise over run. So let's label each one of these. Between 0 and 1 is 32.5. Alright, up 32.5 over 1. And this one's 27.1 over 1, and up 10.2 over 1. Okay, we don't have to label them all. Alright. What I want you to realize that now is, guys, that change in y over change in x, that is really a change in meters over time. So change in distance over change in time. And you fizzy wizzies, you know this is the velocity function. Okay? Velocity is equal to change in distance over change in time. Okay? And change in y over change in x, the rise over run, that's the average rate of change. The slope. Okay. Big time connection here, guys. I need you to focus. Alright? If the average rate of change is the slope, which is the change in y over change in x, all this stuff, which is essentially velocity, what is the instantaneous rate of change? It's the slope of the tangent. And we know there's a function for that. We know there's a equation for that. It's the derivative. So here's what I want you to get right now. The derivative as well, the derivative, I'm sorry, let's back up. Okay, the average rate of change of a position function, change in distance over change in time, that's a velocity, but it's average velocity. Okay, so when you do f of b minus f of a or b minus a, you're actually calculating an average velocity, change in distance over change in time. Now, when I do an instantaneous rate of change, which is the slope of the tangent line, f prime of x, which we don't have a function, but we will. We'll have a function here soon. That is not the average velocity. Alright? That's the instantaneous velocity. Okay? So you gotta see this, guys. You gotta see the slope of a position function is essentially a velocity. And you gotta see the slope of a tangent line, which is the derivative. Let's write this down verbally. Let's get our verbal right, okay? The derivative, of the position function is the velocity function. End quote. We all need to write that down. Okay. Which that's pretty sweet, guys. Now, you should never forget your velocity function in physics for all you fizzy wizzies. Okay? So what we're going to do now is we are going to use this is a quadratic curve, right? And we only have points, so we can only do Aroc. Okay? Let's find the instantaneous rate of change, which means we need a function. So what is f of x? How do we do that? Thankfully, we have a calculator, and you'll never be asked to do this again. But, or maybe, possibly, but I want you to find a quadratic regression and find the function of the the function of this actual position function. So we're going to create an equation. The calculator does that. Okay. So what we're going to do is we're going to go to stat. All right. Calculate quadratic regression. Quad doesn't stand for 4. All right. It stands for quadratic, which is x squared. Hit enter. Our x list should be L1, y list L2. Because this is our x's, this is our y's. We've already put it in there when we did our stat edit. We're going to hit enter, 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 enter. Wow. This is the position function. Okay. So we have a position function, and it's a falling object with the forces of gravity. Obviously, gravity is affecting this. Boom. Let's write it out. Negative, and we'll round to the nearest hundredth just for time's sake. All right. So when we do our quadratic regression, as you all should know, you should have done this before, you end up with f of x equals an a times an x squared plus ab times an x plus ac. You probably won't ever have to do this in calculus, but you got to know where to put a, right there, where to put b, right there, and where to put c. Okay? Now, the reason I'm giving you a position function is so that we can actually find an instantaneous velocity. Okay? Alright. And we're going to find an instantaneous velocity. How are we going to do that? We're going to find the derivative. A couple things of note. Alright? These slopes are positive. That means my velocity is positive. Okay? My velocity should be 0 right here, and my velocity should be negative. Alright, let's go ahead and find the derivative. Alright, so given our original function right there, f prime of x would be power rule, multiply, negative 9.88 x, and that's 1, so it multiplies, plus 38.67. Now, we already calculated average velocities up here. Let's see if we can see if our derivative actually will give us something like this right here. And what would it be though? That's the derivative, that's the average rate of change between 0 and 1. So let's see if we can maybe do the derivative of f prime of 0.5. Okay. Let's see if we can find it. F prime of 0.5. Alright, so we would plug 0.5 in. Okay. No, sorry, I didn't plug 0.5 in. Alright, work it on your calculator. Let's go. Quit. Negative 9.88, and we rounded, so it's not going to be perfect, times 0.5 plus 38.67, 33.73. This, according to our quadratic regression, alright, this is what I want you to be able to do, guys. Alright, instantaneous rate of change. Okay? The instantaneous rate of change is the slope of the tangent line, which is the output of the derivative. So let's get our verbal right. Alright? We would say the instantaneous rate of change at x equals 0.5 equals 30. I'm sorry. Yeah, well, I'm sorry. Is 33.73. What are we doing again? We're doing change of distance over change of time, so this would be meters per second. Okay. And that's the instantaneous rate of change. How close were we on our average? Let's see. Where our average rate of change right here was 32.5. Very cool. one thing else you have to do, and you have to remind yourself of, is when you do an average rate of change, let's take our answer above. The average rate of change on, and this is one thing you have to do, 0, 1 is 32.5. This is a guess. This is exact, okay? But also you have to know that this is also, and this is very, this will be on your test, no doubt. This is an estimate. Oh, I spelled that wrong. It's an estimate of f prime of 0.5. Why is this an estimate of f prime of 0.5? Because we're averaging the point next to 0.5 and the point after 0.5. I'm sorry, the x value next to 0.5 and the x value after 0.5. So anytime you need to do an estimate, you're going to pick these 2 points. Where's 0.5? Right there, right? We're going to pick those 2 points and do an average rate of change. So let's get our verbal right. To estimate f prime of x, or sorry, f prime of, let's say, in this case, let's do another one. Let's say to estimate, in this case, f prime of 1.5, we need an average rate change on 1 to, sorry, comma, or comma, yeah, comma 2. Does that make sense? Because 1 comma 2 is between the 1.5 is between the 1 comma 2. So anytime you need to do an estimate, it's simply an average rate of change on that interval. Get it? Got it? Good. Very important. Okay? Alright, so let's spiral back. Okay? What do I want you to be able to do? I want you to be able to estimate f prime of x with the average rate of change. We talked about it. Here's our verbal. This is what we do. That's the formula, essentially. Average rate of change is this formula. We want to be able to graph the average rate of change. Well, we haven't done that yet, so let's do it now. Okay. Excuse me. I'm going to have to do some finagling. Alright, so cool. Right here, here are x's, here are average rates of change. Okay? We're essentially graphing the average rate of change, which is the estimated derivative. Okay? Alright, so what we would do is we just simply, since we have positive and negative values, okay, and I'm not going to, here we would go over 0 up 32.5. Now we're graphing the derivative using data. Alright, graphing the derivative using data. So over 0 up, let's do 10, 20, 30. Over 0 up 32.5. Oh, no, I'm sorry. Since it's an estimate, since we're estimating the average rate of change between these 2 points, what would it be? What would a good x value be to plot? It would be the one in between, which would be 0.5. I hope you guessed it. That's it. That's it. Alright? So x is going to be 0.5, y is going to be 32.5. X is going to be 1.5, y is going to be 27.1. Let's go ahead and sketch that in your notes. I'm going to pause so I don't slow you down because you're probably faster graphers than I am. And we're back. So here is our x values, time, and here is our graph of the derivative. Okay. Each one of these is an estimated value, an average rate of change. Okay. So make sure you have that in your notes. Okay. Alright, so we have to be able to graph the derivative using average rate of change, which is simply an estimated value of the derivative. Okay. Once again, 32.5. That's the average rate of change from 0 to 1. So we can estimate the real derivative, the real slope of the tangent line at x equals 0.5. Okay. Alright, now simply all you have to be able to do at this point is graph this derivative axis and this x-axis. That's it. There's your formula. It's simple. Okay? Alright. Last thing we're going to do, which I hope it just blows all of your minds. Okay? Spiraling back. Okay? Alright? F prime of x is the instantaneous velocity. The derivative of the position function is the velocity function. What is the derivative, though, of the velocity function? The second derivative. Let's get our verbal right. Alright. And that we're done with that graph because that's all you simply have to be able to do. Right there, we're done with it. Okay. Alright. The derivative of f prime of x, which is denoted as ddx of f prime of x, is equal to f double prime of x. Okay? So let's do the derivative of f prime of x. This is going to be awesome. You busy guys will probably flip. Alright? If I do the derivative to our f prime of x, which we calculated earlier by doing the derivative to the original function, we calculated as negative 9.88 x plus 38.67. Okay? If I do the derivative to this, what do I get? Right there, f double prime of x. And the power rule states that wabam, that's what I get. I get negative 9.88, and that becomes 0. Guys, this is the acceleration due to gravity. So what do y'all think the second derivative, what is the second derivative of the position function? You guessed it, acceleration. Okay? So, here's what I need you to know. Okay? The derivative of f of x when f of x is a position function is going to equal not only f prime of x but also the velocity function. Sweet. And the derivative of f prime of x is f double prime of x, but it's also the acceleration function. basically, last thing, and then I'm going to show you how this works in physics. The derivative of position equals velocity. The derivative of the velocity function equals acceleration function. And there's one more. Oh my goodness. It's called a third derivative. It's kind of funny. The derivative of the acceleration function, which, if you think about it, you take the derivative once, you get velocity. You take the derivative twice, you get acceleration. What happens when you take the derivative a third time of f double prime of x? You get the third derivative, which is the jerk function. So anytime somebody's being a jerk to you, all you have to do is call them a third derivative. They won't know what it means, but it'll be funny. You'll know what it means. Okay. So when in doubt, do not be a third derivative. All right. Okay, so last thing before I give you some practice, and your practice will be a second video, okay? Because I want to end this video. You're essentially taking notes at this point and understanding these three things. But first, let me spiral back, okay? All right, so we need to estimate f prime of x. That's the average rate of change. So if I have 0, 3, x, y, and 2, 10, x, y. If I want to estimate f prime of 1, it's stuck between, that is between 0 and 2. All I need to do is an average rate of change formula. F of b minus f of a over b minus a. Okay, those are y values. This will become f of b, which is 0 and 2 will be a and b, right? F of b will be 10 minus 3 over 2 minus 0, which would be 7 over 2 equals 3.5. So the estimated f prime of 1 will equal 3.5 based on the average value. Okay, now we need to be able to calculate instantaneous rate of change. Once again, that's easy. All you need is a derivative of the position function. Bam. Okay, plug it into the derivative. Alright, let's say I need an acceleration value. Alright, okay, if I need an acceleration value, all I would need to do is to plug something into the second derivative. And of course, can I plug an x in here? No. So the acceleration is always negative 9.88. And for you physicists, you know the acceleration due to gravity is always negative 9.88. And how did we come up with that? We came up with that with calculus. Man, imagine if Sir Isaac Newton had calculus before the apple hit his head. He would have known gravity was negative 9.8. This is awesome stuff. Okay, so, alright, so I digress. We are basically done. I know there's a lot of mumbo jumbo, but these are the three things. I'm sorry, they're not exactly all of them. Estimate, average rate of change, instantaneous rate of change, graphing the derivative with data. All we need to do is calculate some average rates of change. So boom, 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 we got all that. And position, f of x. Velocity, f prime of x. Acceleration, what is it? F double prime of x. Okay, good. Now, last thing. I swear, I'm almost done. Okay. Alright, so last thing, let's go back to those physics equations we were talking about. you'll never need to memorize these equations if you know the regular position function. Okay? So let's see if I have this. I don't think I do. No, I don't. Let's see. I'm going to copy and paste. Okay. Okay. So, bear with me just a second longer. Okay. Alright. This is the position function. Let's take a derivative of the position function. You fizzy people, always worrying about memorizing functions. What is the derivative of the position function? We know it's the velocity function. Power rule, bam, 2 times 1/2 is 1, so it's the gravitational constant times t. Power rule, 1 minus 1 is 0, so t's gone, and I go wabam. So this is just a constant. Those are just numbers. So that constant comes down. Yep. You don't have to memorize that velocity function because calculus. You just take the derivative of the position function, you have the velocity function. Alright? Check this out. If I take the derivative of the velocity function, what do I get? Acceleration function. Sweet. Alright, acceleration function, power rule, well bam, minus 1. Acceleration function is the gravitational constant, which is acceleration due to gravity. Alright, I hope I haven't bored you too much, but we'll have more funky position functions to work with, okay? It's not always going to look like this, and this is probably the last time you'll see all this. Okay, but I just wanted to, alright, well, I just proved the point. And of course, if we take the derivative of the acceleration function, you get a jerk, which is the third derivative. Don't be this guy. I may ask you to calculate this maybe one time this year. But the jerk function is a funny function. We can talk about it in class, but I'm not gonna spend too much time on it. And that's all for this video. Check the next video. It'll be probably a 30-second clip over some practice problems I want you to do before class on Monday. Basically taking some derivatives and whatnot. All right, peace out, guys. Thank you.